then transferring that circuit to PCB. I'll probably be going a little bit quicker, maybe, but there will be some things that I will not be explaining clearly enough. And it's just that I want to get this design finished in this session and then order it so that it does take a couple of days to get manufactured and to be sent over, just so that I have a design and you can see sort of like the whole design process, using a company to create the PCB design, and then physically what are the differences between what I designed and what I actually got back from a company, because it is quite interesting. And then also ordering components, which I also have done. Okay, as always, if something fails during our session, the audio or the video or any other problems, let me know. You can just unmute, send me a message in the chat, even send me an email. It doesn't matter as long as you just let me know that something is up and something is not correct. So I decided last week that I wanted to do the full adder circuit. I specifically use that or like that circuit because it deals with, I will need to integrate a couple of ICs, integrated circuits, with a couple of resistors, LEDs, and switches, and then also a power supply. So it's a good mix of components that we need, and it's sort of it's a nice little simple circuit to start with. So sometimes I don't feel students understand what the circuit's supposed to be doing. That's fine. So the full adder, what it does, it's adding two binary numbers. So it adds a 0 or a 1, adds them together, and you get the result. It also has a carry in, meaning that we can cascade or network our full adders, because they can only add up 2 bits, one at bit A and bit B, and if we cascade them, we can add bit A, bit B, plus bit C, plus bit D. And that's what we're also going to be doing. So as a reference point, I'm sharing my screen. You should see the background of person running, which is great. This terrible picture of the full adder, which you all should have, with the 2 exclusive OR gates, the 2 AND gates, and also the OR gate. Now, as well, I did give the circuit for you guys to try. I trust that you have tried it and have done it so successfully, because if you have not done so successfully, then I would have thought that you would have contacted me to tell me I've got problems simulating. So because I did not hear anybody telling me that they have problems, I then assume that you're all able to draw and simulate this circuit by yourselves. Right. So moving on, I will not be simulating the circuits because we have simulated the circuit and I'm relatively sure that it does work. So I create my Eagle file. I'm creating my schematic. First thing I do in my schematic, I look at my grid. Now I'm feeling strange today, so I'm going to keep my grid at 0.1 inch. There's no specific reason for that. It's just today I like inches. So I'm keeping my main grid 0.1 inch and my alternate grid 0.01. And that is fine. It's not, you can choose whichever type of grid you use. Just make sure that you are always aware of the what grid you are actually using. Right, and then I add in my, because I like frames. And you'll also see, so let's search for my frame. Right. So now I can start adding in a couple of components. So let's start with the exclusive OR gates. Let's search for XOR, which stands for exclusive OR gates. Now we have to start choosing which components we would like to use. I already did a little bit of research, and I know which gate I would like to use. So the gate I would like to use is this one. This is an exclusive OR gate IC. It looks like this. Its footprint is there, and it has 4 exclusive OR gates inside of it. As I was doing my research, I realized, oh, okay, I just need 2, but the IC has got 4. I cannot just order a one with 2 in it. So I'm going to be creating a double adder circuit where I add in 4 bits. So not just the single one with the 2 exclusive OR gates. I am going to be having a cascaded version where one feeds into the other one, which I think is really exciting. So back to the to my screen sharing. So I mean, there are lots of different ones that you can choose from. I like this one. I like it because it's a dual inline 14 package. It is the 74 family of gates. 74, there we go. And let's just see what this is. It's the same one. It's pretty much the same one. So let's choose that one. I click on it. And now we know that this gate contains 4 exclusive OR gates. So it usually starts by giving us the first one, second one, and then the third one, and then the fourth one. So we place down IC1A. So this is the IC number 1, gate number A, IC1B, C, and D. Now we have our ICs. I just want to see these. D. I just want to make sure that I'm doing this correctly. And you can also see if we add more gates, this is now IC number 2, A, B, C, and D, and then IC number 3. If we wanted to have more ICs, but we just need this one. The next thing I did was I actually found this on a website and I ordered this gate. So I'm just waiting for it to load. For some reason, it's really, really slow. Right. So this is the exclusive OR gate. It's 74LS86AN, and it's an exclusive OR gate, and it's got a dual inline package 14, and this is exactly what we are needing. So I have decided, right, I'm going to buy this one. It's 69 cents. So I'm ordering this, and it is the dual inline package 14, which is the one that I need. Brilliant. So that's the gate I'm taking. Next, I need 2 AND gates. Oh, my AND gates. So let's choose search for AND gates. So once again, 74 TTL, that's the one that I like. And let's have a look at this one. This actually looks like a pretty good gate. Right, let's just have a look and see what we have. Alice 08. Right, so let's choose this game. My 74 Alice 08. So, right. And we are placing down our gates. And then once again, we will see the numbering starts again at IC2A, IC2B, IC2C, and IC2D. So they're all from IC2D or from the same IC. And then I've also found it on my no, sorry, this is the OR gate. I don't need the OR gate now. I'm going to search for the OR gate. No. Well, yes, that's actually the right. And I found my IC here. And it's also the dual inline package 14, so I know it'll fit into the one that I'm using right now. Then I need an OR gate. And I settled on the 32N. Right. Dual inline package 14. That is the package that I want. LS 32N, exactly what I want. And now with this, I only need 2. So it's like the other 2 are being are not needed. So I don't need to drag them into my design. Now, the next thing that I need is I'm going to be needing my inputs. The circuit has got a number of inputs. So I first, generally what I usually do is before I start connecting up my circuit, I first draw or I first insert all of my components into the circuit diagram itself, and then I start connecting up devices. Otherwise, it just gets a little bit too complicated. So we are going to be needing some form of input. What's the easiest way of accessing input? It is just by a normal switch. So we are going to be searching for a switch to act as our binary input. So the idea is I will have a couple of switches. That is going to be my input. And then on the output side, I'll just have a couple of LEDs just to show my switch, show my output. Okay, so I'm searching for switches. Now you might see there are a whole lot of switches. And you will have to find a switch that you like. Luckily for you guys, I did do this beforehand. And let me just, I want to get to a diagram. But it is this is usually the case. You have to find a switch that you like. Right. This is more or less the switch that I'm going to be liking. Now, we have to find out how many inputs we are going to be having. So each full adder has got 3 inputs, right? But the second full adder, its input comes from the previous full adder. So we'll only use a DIP 5 switch. This one is perfect. It's a DIP switch. Right, so we select this switch and we place it down somewhere here. And I also found this switch. I also found this switch on the internet and and it looks like this. And this is one I'm going to be ordering. And then when it gets here, this is my switch that I'm going to be using. So that is my switch. The next thing I will need is the something called my pull down resistors. Now, when you are dealing with digital circuits, whenever you are wiring an input switch, you will also always need to have an additional circuit called a pull down resistor network. So this is a little article, sorry, just about pull up and pull down resistors. If you're dealing with digital systems, you will always need these to create your circuits. So I'm using a pull down resistor. So what it basically does is my pull down resistors, when it is not connected via my little switch in this area here, my integrated circuit or my microcontroller, whatever IC I have, is now connected to ground. So it'll read a digital 0. And when I press the switch, it's now connected on this side of the resistor, and it'll connect directly to VCC or 5 volts in this case, and that'll then be a digital 1. It's just a very good, clean way of wiring your switches. I'm going to be, if you want to read up a little bit more on this, I will add the link in the chat. Just have a look at these, if you like, on what pull-up, pull-down resistors are. But I'm going to be wiring my switches in this fashion. So what I need is I set it on a 10 kilo ohm resistors. Now I wanted to see if I can use just single resistors, but I decided against it. I've decided to, not resistors. I am going for a resistor network. Why did I go for a resistor network? Well, I like working with them. Specifically, these resistor networks, that they're just a little bit smaller and look a little bit cleaner on your board. So I could have my 5, well, actually 4 input resistors. No, it need to have individual resistors. I can have my 5-1 as is. Now I did, right. So I'm going to be adding in this, actually a 4 resistor. No, that is not what I need. Now, this is actually a little bit more tricky than you would think. These resistors, let's make sure I'm choosing the correct resistor. There we go. These are the ones I need. Although these are all so this unfortunately is a little bit of the so like the problem with these resistor, that you will have to find the exact correct ones. Right, and this is it. So, right. Now, I made a mistake when I ordered my components. What mistake did I do? Well, I ordered, let me just show what I did. So I made a mistake. I thought, well, I have 4 inputs, I need 4 resistors. So I just bought a 4 kilo ohm resistor network with, and it looks like this, and it contains 4 different resistors. But as I spoke about, I actually need a 5th one. So I need just to have a normal resistor to substitute in with these resistors here. Okay, let's go for a one that looks the same. 2405. This is the one I like. And there. So what this does is now I have my 5 resistors. The next element I need is my incoming power that changes my I will be powering this with a battery pack, so I need a later. And I know I'm going to be using a 78 0 to 5 volts, so it is the 78M05. '78 05. I am looking for, that's the one, the T0220 element. So that's I need, and I will have it here for now. So what is this? It is a regulator. So it takes in a certain amount of voltage and then brings that voltage down to 5 volts, which my circuit can use. It comes in a TO220 package. And this is exactly the one that I have. So I'm happy. I don't need 2. Actually, I just need that. The next thing is I need my outputs. Now, each circuit, they do have 2 outputs. I need 4 outputs. So I'm going to get a resistor network. Again, the same resistive network. Now, if you're looking at the add parts, there's a little arrow down. If you click on that arrow, it shows you all of the elements that you have selected so far. And this is, I can then choose my resistive network. And then I need LEDs for my outputs. Now I have to find the correct LED. Let's go to this one, looks kind of cool. Now I do know that I'm using 5mm LEDs. So that is what I'm going to be choosing. I have 5mm LEDs, and I do know I have 4 of them. So, and I'm also going to be ordering those 5mm LEDs. What are those 5mm LEDs? Well, they are the they simply are the size. You have 3mm, 5mm, 8mm, and 10mm. I've chosen the like the middle 5 mil LEDs. There will also be let's just deal with our circuit as it is now. So I usually like to start from the like the left side and work our way through to the right side. So what do I mean by that? Well, what I mean by that is start connecting from our switches side, start with creating our pull up and pull down resistors, and then go from there. So let's do that now. I actually want this to be here at the top. So we can move around these individual resistors like we as we like. It's not really a problem. So let's have our circuits. So first it runs from VCC, which in our case is our V out. It runs through the switch, and then through the switch, it's then so we have our V out. And we connect all of our switches. So what we are basically doing is we are creating this circuit here for all of our switches. So it goes from VCC through our switch, then it goes on to our devices, and then it also goes down through our resistor to ground. Now, what I also need, let's just search for. So what I'm doing now is I search for the G&D. Remember, we use G&D in terms of for our SPICE simulation. We're also going to be using the G&D for our circuits here, but we are just using the ground just to designate a certain net to ground. So we will be designating this as our ground net. So whenever we want to connect a certain device to ground, then we just draw in or take in that specific ground symbol, and then so like we don't have to connect it to this net here because we have our ground net. You'll see what I mean in a second. It's a little bit disjointed. So we have our first element. So let's start with these R1, R2, R3, R4, and R5. So we can all connect all of these to ground. So I connect all of these to ground. And number one, let's just go to switch number one. Switch number 2, 3, 4, and 5. Now we've connected up our switches in the correct way. Now the next step we should be doing is connecting up our devices according to our circuit. So we're going to be using this circuit and just doubling it. So the two switches A and B, which is number 1 and number 2, goes to my exclusive OR gate. So I'll connect them up So number one. So let's not. And then that output then feeds into one of these ones. Input. And then my third feeds into. Yes, connect up this net. My second now you can appreciate how quickly these circuits become untidy. So you have to keep in mind, you always want to keep and select or create a pretty tidy circuit, just so it's neat and you can understand what is going on. So the next step is now this feeds through. Well, let's just connect the other circuit as well. And we'll connect it in exactly the same pattern as we did the previous one. Now, I probably could have taken the one circuit and just double it. Yes, that is something that I could have done, but I preferred not to do it in that specific way, just as I like to create my circuit. I don't like to redo my errors, so I try and do them, these two circuits, by themselves, just so that I make sure that they are exactly correct. So I'm connecting up my circuits. And the last thing I need to do for these circuits, so this carry from my first adder, this would be my first adder, is then my carry to my second adder circuit. So it will come in here and be the first adder. So this adder, the carry, is coming in from us, from the user. It is fed into my circuit, and then it is carried over into the next adder. Now, the next thing we need to do is just to create our outputs. And these are just our resistors feeding into our LEDs. And then we need a ground termination for our LEDs, or else they don't work. Oh, yeah, the ground. And then we connect up our LEDs. So I realize this is probably not the most exciting thing to be watching, but it is an important way so you can see what actually happens during this process. So this is basically done. What is now happening? So why are these resistors? Why do I need these resistors? Well, those resistors are just there to protect my LEDs. Whenever you connect up LEDs, you need to have a circuit connected, a resistor to protect them. Right, let me just explain. So these are all the components that I'm going to be using. Well, there's one still coming. So the resistors at the start of the circuits, I explained that I'm using them for my pull up and pull down resistors. They just help with the switches and just help to have a very distinct 1 or 0 signal. On the opposite side, I do have my current limiting resistors. Whenever you are using LEDs in a circuit like this, you have to add in a resistive element in series with them. The reason is it protects them from overcurrent and being damaged. If I just use them as is, those LEDs will become damaged. So now I use a current limiting resistor. So that what happens is that resistive element, due to Ohm's law, soaks up or manages the current that runs through that branch. So then what is happening is that then that protects the LED so that a lesser amount of current runs through the LED than with it. So, okay, so there's one more element that I would that I need, and this is a connector. I need to connect my battery to this. So what I generally need is a SIL connector. So what is a SIL connector? Well, let's just have a look at connectors. So now connector is probably one of the biggest connectors that you can have, and you will have to wade through and see which connector works for you. Now I know the one that I like, or the one that specifically needs this. So what am I talking about connectors? What is going to happen with this? Well, this connector is just where I'm going to be having a let me just show you actually. So these are all the components that I have ordered. I'm going to be powering my pack with a 9-volt battery while that's loading, and also it's going to be why did that happen? That's interesting. So this 9-volt battery is going to be connected via a wire like this. And these wires I will just simply solder onto my board. So I need these holes is actually what I need. I just need a connector with these holes so I can easily solder on my battery connector. So I like this one. I will insert this connector here, and then one will be my input voltage and the other one will be my ground connection. Brilliant. So what I need to do now is I need to name all of my nets. Well, before that, let's just give our components the specific value. This is a 10K resistor pack. See, they are all 10K, and this is my lone wolf resistor, which I forgot I needed. And these are, I think, 220 ohm resistors. This LED, I think, will be green. This LED is going to be red. So why do and this LED will also be green. And this LED will be red. So I'm doing it like this so that the LED, the sum LED is green and the carry is red, so I have different colors. And now I've named pretty much all the values I need. I can now start naming my nets. So let's give these values. right. So it's a good idea to name all of your nets. So this is my V underscore, oh, let's just call it V in. This is already my ground net, perfect. And this is my VCC. So what is VCC? Well, it is simply the incoming power. This is my A connection, B connection. This is my carry in. And this is my C net and my D net. So why am I naming all of my nets? Well, I'm naming all of my nets so that on the next step of my design journey, I know which nets I'm using or what those nets mean. Exclusive or 1. And this is exclusive or 2. So give them names so you understand what they do. And 1, 2, and 3. So I'm giving them names so I know exactly what those nets are performing, what they are doing. This is output 1. Let's redo this. So this is my sum 1. Oh, I need this. This is my carry in 1. This is my sum 2. And this is my carry 2. I also need to name this little net. This is called out 1. Out 1. Out 2. Oops. Three. And out 4. Oh, wait, I need another component. So I have just dragged in a component called VCC. What is VCC? It basically is the voltage input of my integrated circuits. So the integrated circuits, as you might know, they come in 4 pins, the specific dual inline package 14. They've got 4 pins. They also have a power pin and a ground pin. Now, Eagle, you can draw in or use the IC with the specific IC symbol. I have not done so. I'm using the AND symbol. So what is happening is my ground and VCC connection are being connected in the background. So my VCC as long as I designate a net called VCC and a net called ground or GND, my IC will automatically connect. But don't worry too much about it. I'm just going through this stuff really quickly. And then once I've done this design in the next classes, I'll go through this a little bit more slowly. I just need to get this done. So we have a 5-minute break. And then after the 5-minute break, we will continue on with a couple of things that we need to do. See you in 5 minutes. Given them all values. Now there's just a couple of steps to do before we go into the PCB design itself. And without really knowing it, we have created a power circuit, our power input for our 9-volt battery. We've created the input circuit, the circuit that does actually work, and an output circuit. So our circuit has got these 4 elements. I'll just show them to you quite quickly. So this is my power delivery part up here on the left side, where it will be my 9-volt battery going into the system, and then transferred to 5 volts. And then through this is my input circuit. This is my circuit that does all the work, or my logic. And then I have my output circuit. So I have power, input, main circuit, and output. Now, the next thing I need to do is here's a little button called ERC. It's also, I think, Tools and ERC. ERC stands for Electrical Rule Check. It will give you, it will check your circuit for electrical compatibility, if everything is connected correctly, and it'll give you a couple of errors. In our case, we do not have any errors because we connected up everything quickly, but we do have a couple of warnings. What are these warnings? Well, you click on them and it tells you, well, these wires are very close to each other, but they are not connected. In our case, this is fine. So we can approve that. We approve that. It is fine. It happens if the wires are really close to each other. It just asks you, do these need to be corrected or connected? No, we don't. Those are just fine. It's me. Right, that's fine. And you just have to go through all of this to make sure that that is net C in overlaps pin. That is fine. Frame has got no value. That's fine. I don't really care about that. And this AC has gate unevoked gate C and gate D. Now, what that means is that this IC, our OR gate IC, has got 2 gates that we are not using. We are using the A and the B, but it also has a C and a D one, but we're not using it. So that is fine. Part SLI1 has no value. Well, okay, let's give it a value. It's just a switch, but it likes to have values. SW1, and also this is SW1. No, it's not the switch. It's let's call it V in. And what else was it? SW1 has no value. This is just my input. And we now have electrical rule check. It's checking everything. Everything is approved, and there is nothing that we care about. Okay, so let's just save our circuit, and you will see it's my full adder circuit, and the date and time which I last saved it. Great. So there are a couple of things we can do now. We can export a couple of things. We can export the net list. We'll have a look at that. We can export a parts list. What does that look like? Actually, I need to specify where I'm going to be saving this. Parts list. And I have to navigate to where that is. And this is the parts list. What this does is it gives me all of the parts that I used during my project. And now I know that I need to buy all of these parts. My ICs, my regulator, my green, red LEDs, one 10K resistor, a network of 4 10K resistors, a network of 4 220 ohm resistors, my voltage in connector, and also my switch input connector. Now, that is basically what we need to do on this side. Now, let's just make sure everything is saved. Now, what I need to do is I need to go to switch to my board. I can either click here, switch to board, or I can click on this button here, generate or switch to board. So I click on that. It tells me, oh, this does not exist, create from schematic. I'll tell it, yes, created from schematic. And now what we are now treated to is this board here. Now, just a quick explanation. These are my components that I are going to be, that I am adding to my board. Actually, before this, I'm just switching back. I want to add in a bit of text. And just to show you, test board. And I want to have it on the nets layers. Test board, and then also I want to have test board once again, but this time on the names layer. So what this will hopefully do is test board will now be created in copper, and the test board will be created on the silk screen layer for which all of my components then have their own unique names on the layer. And I'll just want to do this so that you can see the difference between these two options. So let's switch to board again. Right. Back, that is there. Okay. Now, these on the left side here, these are all of my components. And on the right side is my board outline. So I can designate any type of outline that I want. It's on the dimension layer. But once again, let's just have a grid. This is now in mils, but I like millimeters for this because the manufacturer has got its elements in millimeters. So the first thing is my manufacturing company uses, tells me I can have a 880 by 100 millimeter board. So what I do is I do not want this. So I delete it. And I create my own board. So I create a line. I select the dimensions. And I click on this. I want sharp lines. I want my board to go to the X value. Work. So, and then back to. So what no, don't worry about this. I will go through all this in detail a little bit later when we are going through this. I just need to finish this design so I can order it. But what I've created is basically the outline. So this black space here is where I can add in my components. So my first component, I'll have a look at my elements here. So the first component is the V in. I'll first do the power delivery. Now I do have to look for these components. So this is the V in component where I will be creating my element or have my before I do that, where my power comes in. Firstly, I would like to do some options, view. Let's just have design rules. So design rules, I'm not going to, like I said, I'll have a look at this on a slower date a little bit later. I will have a layers, distance, sizes, minimum width is 100 mils. No, I need a little bit thicker. Let's have a 10 mil. Right. I'm just setting the minimum width of my components, but like I said, I'll go through this a little bit later. This is my V in. Here I have my component. As with everything, you can quite definitely manipulate the components as you like. It's the same thing as with the schematic. I can select them and move them. Let's have this component standing here. The next thing I need is, if I go back here, I probably need my switches. So I have my switches moving in here. And then my resistor network of 10Ks. that is the wrong one. So this is my 86 resistor network. Switch, resistor networks, and these ICs. Okay, so IC 86 is also another one I need. Let's move it. Now you will see that these are the yellow lines are what we call the rat's nest, meaning that it's it has it looks like a rat's nest because it's so unorganized, but we drag in our components and then we make it organized for ourselves. So this is this IC. The resistor network looks good on this element. And then my LED, which is my one output. My second output. My third output. My fourth output. And then R1 is my little lonely input LED there. So now I've got a very, very, very difficult to look at circuit. So I can see now I don't need this much space, right? So what I can do is I can select all of my components as we always do, select all of them, click on move, right click, and then move them. Oops, Daisy, that is probably not great. So what happened there is that I selected my dimension from my board, which I don't necessarily want. So I select of all my components, click on move, right click, and then move them here. Now I can see that my board does not need to be as big. So what do? I delete the outline of my board. You do not need to be that big. And I draw a new outline. Which looks something like this. Now I've drawn in all of my components. And now I can see, click on manufacturing, and it gives me a preview of what my board looks like. So I can see all my components are on my board. So I can see the pads and the silk screen, and this is the top side, and also the bottom side. Looks like this. Now I can I can fill in some elements of my board. So now I need to connect all of these wires. See, these are called a rat's nest. They're also called an air wire. So this means that this is not connected. So I can connect these by clicking on clicking on this. I can select which layer I would like to connect this on. I want to connect it on the bottom wire. And I then click on the element I want to connect and then connect it like so. Now I have created a wire, and you can see it's called VIN, which is the net name. Click on manufacturing. It's not there yet. There it is. See there, I've now connected those elements. So now I can go around connecting all of these elements. But since we do not have that much time, I'm going to be using a tool called the Auto Router. And I will ask it to route my elements for me. What does that do? Well, we'll talk about all that in a little while. So, right. So now this is kind of the easy part, not the easy part, but it's like the end of our design process. So what this is going to be doing, now that we've dragged in and positioned all of our components where we would like them, we then route them. So then we click on elements to route or to move our components in such a way is that we will have, or we can have an element, or we have a connection. So now usually I would route them individually. That is generally a better way of doing it. But Eagle does come with a feature called an auto router, meaning that you can tell it, please do all my connections for me. And that has just finished. I'm sharing my screen again. So now I have my auto routing results. I can choose which one I would like. So I like this. So it created 4 types of connections. So I like the look of this connection. I think it is fine. So I end my job. And now I have created a connection. All of my wires are now connected. And that is wonderful. And that is perfect. And you can also see my ICs are also connected. So I think this is the VCC connection. You can see it's connected to VCC. And there is the ground connection. So all my ICs are automatically connected because I created a net called VCC and a net called ground. If I click on manufacturing again, you can see that everything is connected or looks connected. And this is what the board should look like. Now let's just add in, you might see that this writing we've created is not carried over to our final board design. So we will have to just add that by ourselves. So we click on text, and here's our first board. So we add in this text, and then also let's add in this text as well. But we shift this to a different layer. Oh, we cannot select this. This is not really that bad. So this is what it should look like. This is our first board. Brilliant. So we have text as well. Let's move on to a T names. and have this. This is our first board. So now, and we go to manufacturing. This should be in copper. This is our first board, and this is our first board. And then we can also have a version 1. Down here. So this is now, we can now send this design to our PCB manufacturing company, and they can manufacture it for us. Oh, excuse me. As you can see, the red indicates this is connected on the red side, and the blue is connected on the blue side. Now, what I can also do is, let's create a at the bottom side. Let's create a polygon. Correct. And then right. And then also I'll talk about what I just did. So I created a net on the one side. Let's see what this does. So what I've just created, I drew a polygon, like a shape around this, and then I told this polygon that inside of it you are. Let me do this then. So I draw a polygon around my board, and I make sure it intersects, and I tell this what signal you are going to be doing. I click on rat's nest. So what does this do? Don't worry so much about this. I'm rushing through getting this design finished within this class, and then ordering it and having it done. And then the next class, we'll go through this slower, and I'll explain what I'm doing more. What I'm doing now is I'm creating a common signal for ground, because you have to remember the PCBs are created. They start from a piece of copper, and then we take away the copper to make our circuits. So what I previously did, if I just so like have it like so. Let me just share my screen again. I click on manufacturing. Now all of the copper needs to be removed to have this one circuit here isolated and created. So it needs to remove all of the copper on the board, which takes very, very, very long. So what I tend to do is I fill in the copper of my board. What then happens is it only needs to, in this manufacturing element, it just needs to take away that small bit of copper instead of all of the copper to be able to create that circuit. So I use this method by creating a polygon and then also creating, giving that a net name. So that means that all of the copper does not need to be removed, and it doesn't. It is still retained within the PCB, and it just speeds up the processing time of this. So now instead of it removing 95% of the copper, which takes very long, it is now only removing about, I think, 10% of the copper. So I will be going through this slower in the next couple of classes. But like I said, I just wanted to create a circuit right now, really quickly, and then spend some time. We'll spend some time a little bit later, just so that we have a, we'll go through this a little bit slowly, a little bit slower. Like I said, I just wanted to create the circuit, have it manufactured, and then we can have a look at it and see like, oh, this is what I did, or I made a mistake, this is not right, this is so, this is this, and all those type of things. But yeah, so this is my board basically done. So the PCB step is relatively simple. I feel it's relatively easy. But this is generally a simpler design or a simpler circuit. And we can try now and see if we can get this manufactured. We should not have any problems manufacturing this. It's this board should be relatively easy to manufacture. There's no, I haven't got any special requirements. It is just going to be relatively simple. I'm going to be using this manufacturing company here locally in Germany. And it's a relatively, I haven't tried them before. This is the first time trying this specific company. But it is a relatively good company, meaning that it can create 0.1 millimeter tracks, which we are staying inside of, hopefully, yes. And then it takes about 4 working days for my PCB to be delivered to me. So that's hopefully within 4 days. So I should have it by next week. And this company can do up to 48 layers of rigid, 10 layers flexible. And this is all of the elements that we can have a look at, or what they can have a look at, and so on. So now I'll send this design to them, and then we will create my circuit. So I do understand it is relatively boring looking at somebody creating a circuit. Fine. But it is important. So what I've just done is I've gone from a schematic, well, an idea for a circuit, created the schematic, and then created the PCB. I've also made sure that the components that I'm using are components I can actually order and are available. And I have actually ordered them before. So hopefully the components will get here. We'll have a look. We'll have a look through at what the components are and how they work. And then hopefully when the PCB comes in, we can have a look at what the PCB looks like, what our design was, and then we'll have a talk about what it looks like, what went wrong in our design, because there was a couple of mistakes. That will only come to light a little bit later, and then we'll talk about everything that I have done so far. So in Wednesday's class, we will start by looking at the PCB process. We'll create a simple circuit and then look at at the PCB menu and how to change things there. So don't worry if some of these things I did today was like, what is he doing? I don't understand. On Wednesday and also the class following out on Thursday, we'll go through all of this a little bit slower. And it's the hardest part for me is usually the schematic design, because there you have to make sure that your circuit is fully connected. But if it is fully connected and you spend time creating a working circuit and everything is labeled, all of your nets are labeled, all of your components are labeled, then going into the PCB element or the PCB part of it is relatively simple. But like I said, we will have a look at all of this a little bit later. I'll order this and then hopefully I can get it made and we'll have some fun looking at it and then also critiquing the mistakes that I have made. But this is how quickly it can go. Right. I'm going to be sending the link for the next class right now. So you have it for Wednesday. And I'm going to be ending this class with you here today. And like I said, on Wednesday, we'll continue looking at the things that I have just did. And we'll slow it down, talk about more what I am doing and why I did it. And yeah, hope you enjoyed it or stayed awake at least, because it is a little bit boring looking at somebody creating circuits. But yes, I'll send the link right now for the class on Wednesday, and I see all of you on Wednesday. Have a wonderful Monday. I hope you have a great start to the week, and then see you all Wednesday. Bye-bye.